Hi, welcome to the start of topic 3, trigonometric functions. But what's going on here? Radian measure of an angle? What's that? Oh, let's come down here. That's what we're used to. Measuring an angle in degrees is amount of opening here in degrees with a protractor. Oh, that's something that's familiar. But all this other stuff, what's going on here? Radian measure. Maybe something to do with the radius of a circle, something like that. Well, let's get into it and see what the radian measure of an angle really means. So let's review what we know so far. Oh, here it is. This is familiar territory. Measuring angles, degree measure and radian measure. Now, this is the interesting one now in this course. So let's have a look at what the basic idea of a degree measure is and get our head around that. So here is a circular protractor measuring angles. And what does it go up to? Well, it starts at 0, and if we go round, there's 350 there, and it comes back to 360. So this is based on talking about a revolution, that is, turn around once in a perfect circle, being split up into 360 degrees. These little dudes here. There's 360 of them in a revolution. We're going to go down in a minute and take some screen clippings from Pearson's textbook for this new IB course first examined in 2014. And have a look at some of the history to this. The Babylonians were responsible for much of this. So then, of course, we use usually a semicircular protractor like this one here to measure this amount of opening, and we call them degrees. Okay, portions, 1/360th of a revolution. Okay. Let's look at a bit of the history of that so that we can move on and see why we might use a different method of measuring an angle. So here we are. The convention of 360 degrees for one revolution can be traced back 4,000 years to the Babylonian civilizations. Now, they didn't use a decimal system. They used base 60. Ah, that's interesting. 60 seems to be an awkward number, but it's the smallest number that has all these factors, 2, 3, 4, 5 and 6. It also have factors of 10, 12, 15, 20 and 30. No one's really certain here about why they chose 360 degrees. Obviously a revolution was important. They could see that the Earth was revolving and so on. I think they could at that stage, not sure about that, but a revolution was obviously an important notion going in a complete circle. So here they assign 60 divisions to each angle in an equilateral triangle, and exactly 6 equilateral triangles around a single point. So that was their revolution idea. So therefore we got 360 equal divisions. So that's an interesting theory. No one's actually sure about why it turned out that way. But anyway, there are few numbers as small as 360 that have so many different factors. And so you could divide a revolution up into quarters. That'd be 90 degrees. A 6, which would be 60 degrees. So it was handy to break down a revolution into those fractions. So I guess it's back here, the idea of factors of this number, meaning you can break it down into proportions very easily. Okay, so that's where we got one revolution is equivalent to 360 degrees. There we have it. All right. Well, what's wrong? Why do we want to change this stuff? Okay, let's have a look at an idea here. Okay, so I'm going to answer that question first. Why might you prefer to have a different measure of an angle rather than the degree of opening? Well, let's look up here at these diagrams. These diagrams are trying to show you that an amount of opening in the centre maybe could be connected to the arc length and the radius What connection could we make there? Because then, let's go to modern times. Let's say we had a satellite moving across the skies from this point to this point over here. Wouldn't it be nice to say how far had it gone, or how fast was it going? If only we could sort of measure or connect this amount of opening to arc length and radius out there. Quite clearly, you can't measure the angle here by just the arc length, because look at this circle. Same angle theta in these three circles. So they all have different arc length. But something that is interesting, and this is what we're going to prove now, if you use a measure of angle theta as arc length over radius, then that is constant for any angle in a circle like that. So we're bringing together the idea of a revolution, but relating the amount of opening here, 3 stars so far, the amount of opening to arc length and radius. That could be interesting if we wanted to see how fast that satellite was travelling across the skies in orbit around the Earth. We'd know its radius. If we could have a different measure of the angle theta relating to arc length, we could actually work out that arc length for the time we observed the transition of the satellite in orbit, and maybe work out its speed. Hey, this is interesting. But what we have to do now is to establish that arc length over radius will give us a constant measure of an angle. Obviously, you can't just go across here again, this one, and this one. You can't just use arc length, because for a set angle in the middle, theta, you would have a varying measure. No good. Let's see if arc length over radius gives us a constant measure. So down here, right down the bottom over here, let's have a look. And so we've got measure of angle theta in this little dude here is arc length S1 over R1. Do you agree? Okay, so now here's an expression for S1. It's the circumference times theta over 360. Do you agree? If theta is in degrees, what fraction of a revolution have you got? You've got theta 3/60ths. That's the portion represented by that degree of opening in there. It's theta out of 360, that's your fraction. Like we were finding out before, the Babylonians used 360 probably because it was divisible into various sections more easily. It had more factors, that number. So theta over 360, portion of the circumference. That's our arc length, isn't it? It's that fraction of the circumference. Now, what is the circumference? The circumference is 2 pi r, so the arc length is that fraction of the circumference. The circumference is 2 pi r. We just have to come down a little bit here. And now, what can we say? Well, let's do some cancelling at this stage, maybe. 2 into 360 is 180. So we've got, let's put this in front, theta times pi r over 180. All right, do you want to finish it off yourself? Want to finish it off yourself? Maybe pause the presentation and say the measure of angle theta in this new idea of arc length over radius would be this thing divided by the radius. Oh, I should be using R1 there, shouldn't I? Okay, theta times pi R1 over 180. I want to pause the presentation now and see if you can work out what S1 over R1 comes to for our angle theta in this little circle. All right, here we are. I'm going to go on with it now. So it's S1, which is this thing, over 180 divided by R1. We've got a little bit more room down here. And so it comes to, well, what's this going to be? Theta pi r1 over 180, and we're dividing by r, or finding 1/2 of it, r1. So that is theta times pi over 180. If theta started off in degrees, okay, it would be theta in degrees times pi divided by 180. That would be our expression for arc length over radius in the little circle. Does it have r in it or s in it? No. So it is independent of r, the size of the circle. Let's do another one. Do you want to try it for this one up here? This is S2 over R2. What we need to show is that this size angle theta, we're saying the angle theta in each of these circles is the same size. So can you go on with this one? Can you show that the measure of angle theta still remains the same? And then again in this one, even in the bigger circle, no matter what size circle this angle finds itself in, it must always have the same size if we're going to invent or discover a new way of measuring the size of angle. We've got to be constant for that constant size of the angle. Okay, you might pause the presentation and try and do those. Right, I'm going to come back and do it now. Here we're going to substitute for S2 the arc length, so it's a proportion, so this is R2 now, and what portion of the whole revolution have we got to get that arc length? Theta over 360 divided by R2, and that's going to cancel. Got 2 pi theta over 360, which is 180 there. So theta in this new measure, here we are, the new measure of arc length is your old measure, theta in degrees times pi over 180 degrees again. It looks like we can convert this angle theta to a new measure. See, we're getting the same answer. That one and that one are the same. So it is, looks as if it is constant, isn't it? Can you see that it will be? Because S3, that in this big circle up here now, the arc length is bigger. Here, the circumference is bigger, 2 pi R3 by, what's the proportion? Again, theta 3/60ths of a circumference we've got. That's how much opening we've got. And if we divide by R3, it's all going to happen again. It's going to be times pi over 180. So, what have we just proven there in a general case? Is that the measure of any angle theta in radians, now you can put that, Pearson says there isn't a unit called radians, and there isn't, is there? But we sometimes use this symbol to indicate that's the form of measurement we're using. It's arc length over radius, and it will always come to theta in degrees times pi over 180. Now that's powerful. That's powerful, because what that means is if you change your angle in degrees by dividing by 180 and times by pi, all of a sudden you have a connection to arc length over radius. And you can actually find that arc length out there. Okay, shall we do a little example? We've got some coming up with Pearson, but let's do it now because it's getting exciting. Let's say you had about 60 degrees, you were watching here for a period of time, a satellite going out there, so arc length S over radius. Now, arc length over radius is the radian measure, so S over R is the radian measure. Now, can we change the angle? It's only arc length over radius if we change the angle to radians. What do? We take our angle, divide by 180 and times by pi. So this comes to pi on 6 radians, which is really just a ratio of lengths. Hasn't got units in actual fact. When we say radians, we're talking about this form of measure. So actually the arc length for an angle of 60 is pi on 6 times r. Yes, r. Yes, well, if r was, for example, 10 centimetres or 10,000 kilometres, whatever radius you might look at, then you could find the actual arc traced out by the satellite or by the moving body once you get it in radians. Once you make this connection, arc length over radius, and here's your connecting formula. What is it? The angle is taken as a fraction of 180 and times by pi. Hey, that is powerful. Are you excited? This is very important stuff later on when we look at going further mathematically in calculus and in motion problems in general. Okay, come on down and let's see what Pearson's got to say here. Alright, so here we are, the basic definition of a radian measure of an angle. Here's the angle traced out at the centre, and if theta is going to be 1 radian, it means the arc length over radius must be 1. So if S is equal to R, it traces out 1 radian. Okay, so we're going to come and have a look at what the size of that angle is approximately. It looks like it's about 60. So we'll come and have a look in a minute. When the measure of an angle is, for example, 5 radians, come up here now. The word radians does not indicate units. It's a form of measurement. It's saying what we're doing. We're going to measure arc length over radius and look at the amount of angle there, not as amount of opening there. We're not going to look at how much opening it is, but rather the arc length over the radius. Okay, so we can have a connection right out there to that arc length. Okay, if the measure of the angle is in units of degrees, we must indicate this by word or symbol. So that's like that. When radian measure is used, it's customary to write no units or symbols. There is a, let's say here, 10 radians, or let's take less than that, let's take 5 radians, like they have 5 radians. You can put a C. That's not usually used anymore, but here we would generally use theta just equals 5. Okay, so the radian measure is a ratio. Here it is, a ratio of lengths, and there aren't any units as such. And this is going to be important in modelling with trig functions later on, where we don't want degrees, etc. We want ordinary plain numbers. Okay, we'll see that a bit later on. Okay, come on down. Let's develop this a little bit and see what we can do with it. Now, usually when we define things, we have a standard, don't we? And so one of the standards in this sort of work is what's called the unit circle. The unit circle is, as it suggests, a circle of 1 unit radius. There it is there. So these points here, in the x direction, 1, 0, and neg 1, 0. In the y direction, 0, 1, and 0, neg 1. Just reinforcing the idea that we have a circle of 1 unit radius. And so we would usually start defining our work on that 1 unit radius circle. So let's have a look at what Pearson's have got there. Now, 180 degrees is pi radians. How did we get that? Well, we said if we want to change an angle theta, it is arc over radius, but it comes to theta over 180 times pi. So therefore, of course, what we're saying here is if you have 180 degrees, the measure of 180 degrees in radians, really shouldn't write that, is 180 over 180 times pi, or just pi, because what are we talking about? For 180 degrees, we are talking about, hang on, we'll just get rid of that, we're talking about here 180 degrees what would be its arc over radius? Well, the arc is, of course, 2 pi r, and it's a half of that, so it's pi r over r. Do you get it? 180 degrees is equivalent to pi radians. Okay, its arc over radius ratio would be pi. And so you could say 1 degree is pi of 180, 1 radian is 180 over pi. Just different ways of actually looking at it. So therefore, you can say if 1 radian, let's just scribble that out, 1 radian is 180 over pi. When you divide 180 by pi, you'll get 57.3 degrees. So you can go backwards and forwards, and there are 2 ways of looking at it, I suppose. Doing this, theta in degrees over 180 times pi, or simply say 180 degrees is equivalent to pi. You might put a symbol there, pi radians, to show the conversion of that, or just write the word. Okay, so in the unit circle, what can we say? If, let's say, this is about, it looks about 60 degrees, if that's 60 degrees, 60 degrees is equivalent to, what is it, it's a third of 180, so it's equivalent to pi on 3 radians. Now, if the radius is 1, then arc length over radius is pi on 3 over 1. So we can immediately, in our standard circle, say if the measure of the angle theta is arc over radius, then it's in radians, then it's arc over 1. So if you measure the angle in radians here, so 60 degrees is this, pi on 3 radians, in a unit circle you automatically have the length of the arc. This is pretty good fun now, just to play with these ideas. The equivalence, look at this. The equivalence, 3 signs in maths means equivalent to, the equivalence of those two are very, very handy. Okay, so let's have a look and do some work with this now. Here's an example. The angles of 30 degree and 45 degree and their multiples are often encountered in trigonometry. Okay, and I guess that's why the Babylonians wanted a measure of a revolution in a number which accommodated or was a multiple of 30 and 45. They are common ones because, of course, 30 degrees is a sixth of a revolution, 45 is a quarter. What is 45 as a fraction of 180? What do you think? Of 360, sorry. What is it? It's an eighth. Okay. So here, and I said this was a 6, this is a 12 of a revolution. I was talking about 180 instead of 360. So this is an eighth of the whole circle. So the multiples, they're often encountered in trigonometry. Let's convert those to radian measure and sketch the corresponding arc on the unit circle. And use these results to convert 60 and 90 to radian measures. So let's come down and have a look. Okay, so here we are, 30 degrees. What do? 30 over 180. This is a 6. Oh, they've gone to it there. So it's pi on 6. And if you sketch that, 30 degrees in there is equivalent to pi on 6. And in the unit circle, if this is in a unit circle, that would be a length of pi on 6, because arc length over radius in the unit circle is equal to just the arc length over 1. And this is the measure of angle theta in radians. So, if you get pi on 6, you've got the arc length directly. Let's go down to 45 degrees. What do? Divide by 180, find the proportion of pi, which is pi on 4. So this 45 degrees in there can be thought of pi on 4, and this arc length, therefore, the measure of the angle in radians is equivalent to arc over radius. So pi on 4 is equivalent to arc over 1. Oh, as soon as you've done this conversion to radian measure, you automatically in the unit circle have also discovered directly the arc length. Let's have a look down here. Since 60 is 2 times 30 and 30 is pi on 6, then this is 2 times pi on 6 or pi on 3. So we're looking at multiples now, reaching out to other angles using this method. So 90 degrees is 2 lots of 45. 45 is pi on 4, so 90 is 2 times pi on 4 or pi on 2. Now let's have a look at this note over here. This is very, very important in maths. It's very helpful to be able to recall the results here because they are such common angles. So we're going to think of 30. You need to basically memorise that as pi on 6. 45 as pi on 4. And so you might look at all the multiples of that. So 225 is 5 lots of 45, so it's 5 pi on 4. That sort of flexibility. I mean, you could always go back and say 225 over 180 times pi. You can do that. And then cancel by 45, so it goes 4, that goes 5 pi on 4. 11 pi on 6, what's that? 11 lots of pi on 6. Pi on 6 is 30. So you've got to be moving around backwards and forwards depending on what you want in your particular problem. So please remember 180 degrees is equivalent to pi radians. Okay, we don't usually use that symbol in there, but that's your measure. I give you, let's say, 60 degrees. You say, oh, 60 degrees is a third of that, so it'll be pi on 3. That sort of thing. Be flexible. I mean, you can always base up here, you can always base it on measure of angle theta is arc over radius, which is theta in degrees over 180 times pi. That's the basic definition. So if you've got 180 degrees, you've got pi radians, and any proportion of that you can work out as a proportion of 180. Do you get it? You might have to stop and think, but it is useful, isn't it? Can you see the idea of knowing what's going on, knowing what's going on right out there by measuring the angle? So you could watch your satellite and measure over a period of time that it went through 45 degrees. That would be the easiest with a clinometer or something like that. And then convert it, and then you could immediately find that arc length and how fast it had travelled in that time. Okay, powerful stuff. Let's come down now, have a look at another example. So here, convert the following radian measures to degrees. But must be able to interpret both ways. Express exactly if possible, otherwise express accurate to 3 significant figures. So let's look at the first one here. 4 pi on 3 is 4 times pi on 3, 4 lots of 60, 240. Or 4 times 180, pi is 180 over 3, and do it that way. Either way. Okay, so neg 3 pi on 2. What might negative mean? We'll have to have a look at that. Negative 3 pi on 2, neg 3 on 2 times pi, and neg 270. And then 5 here is 5 radians, so it's 5 over pi times 180 degrees. Okay, so the same thing again, converting it. So here you need to say, well, here 138, what fraction of pi is it? And then multiply by 180. Okay, so it's more this style here. Okay, so have a look at those, and we usually use 3 significant figures like that one there. Okay, let's convert the following degree measures to radians. So degrees here, well, you could put it as 135 over 180, that fraction of pi. or you could think of it as multiples of 45, because you know, hopefully you'll memorise 45 is pi on 4, 30 degrees pi on 6, 60 degrees pi on 3, 90 degrees pi on 2. You'll get used to that. So neg 150 is neg 5 lots of 30, which is neg 5 pi on 6, which is that there. Okay, or doing it as a fraction of 180. Remember, 180 degrees is equivalent to pi radians. So if you've got 175 degrees, you want that portion of 180 then times by pi, and 3 significant figures, because this doesn't go exactly there. And then 10 degrees, what portion of a pi have you got? 10 180ths. So this is your tool here. So if you're in pi land, you want source for that? Oh, different pi, sorry. If you're in pi land, then you're going to say what fraction of pi have I got, and therefore what fraction of 180. If you're in degree land, you'll find a fraction of 180 and change that to that fraction of pi. And there could be decimal fractions there. All right, some interesting things happening here though. Let's just watch here the idea of the unit circle, because we want to do this later on. We haven't done it yet. So if, for example, not much of a circle, that one, mate. Okay, so let's have a look at this idea of neg 270. How can you get a negative angle? Well, we think of going positive angles that way around the unit circle, and negative going that way. So neg 270 would be that's neg 180, and around there would be neg 270 degrees. So we just mentioned that convention now, because for the first time we've seen the idea of a negative angle. And you always remember in mathematics, negative means the, I won't say reverse direction, let's put opposite direction. So the opposite direction. And what we must remember here, by convention, around the unit circle we usually start here and go upwards. So you would remember that from the diagrams just above. We were talking about angles starting there like that. So we think of that as the positive direction, and therefore neg 270 would be working back this way in the negative direction. So we'll be doing a bit more of that. So just a few conventions coming in there. All right, let's come down and have a look at the calculator. All graphics display calculators will have a degree mode and a radian mode, and this is very important here. Most of your work this year in this course, and next year particularly, will be in radians. So please make sure, particularly if you lend your calculator to somebody else, that the mode for the angle is in radians. Okay, you will find later on, as Pearson's are saying here, the radian measure, particularly in calculus, where we're finding rates of change, is the preferred and very useful mode, because we're going to be doing things like modelling as well, where we're going to try to use trigonometric functions, sine, cos and tan, to actually model or make a practical mathematical description of a practical situation. So that's going to be important there. Alright, so how do you find it on the calculator? Let's come over here, the Casio. First of all, you need to set or choose run map mode. So you come to this window here. You now need to go into the brain of the calculator, come down here, see it there, it's set up. So you need to hit shift and the button menu to go into the brain of the calculator. You then get this window here, and you can see down here an angle setting, angle in degs. Okay, so that would be what you've usually used now. So if you use this button here and scroll down, you can highlight angle and degs, and up come the options. Here they are here. Okay. Degrees you know about, degree of opening. You now know about rads, so you want radians, so you'll hit F2. Gradians is used in engineering, so you probably won't use that in this course. So we'll set it by hitting F2, and this line will then change to radians, and then you exit that or hit execute and you come back to run mode. So check that your calculator is in that radian setting for things like trig functions or any work with angles. Okay, let's go on now and have a look at some ideas that have come out, I suppose, of this ratio of the measure of the angle theta is arc length over radius. This is our new measure. And what does that mean? Well, if we have an opening here of 1 radian, what it means is arc length over radius is equal. It comes to 1. Okay, now we know that 2 pi is equivalent to 360, isn't it? Remember, because 180 or pi is equivalent to 180. So a whole revolution, 360 degrees, is 2 pi. So what we're going to say, therefore, is what is 2 pi? 2 pi is approximately 6.28 to 3 significant figures. So what have we got there? If we have a circle with radian measure, we'll have 6.28 radians. So there'll be how many, if the radius is r and it's 1 radian, arc length over r must equal 1. So this will be 1 radian, one radius here, another radius, another radius. So this is an interesting result. 6 radii worth around the circumference and 0.28 in there. So it's a little bit more than 6 radiuses worth around the circumference. Just an interesting little result there, just reinforcing the idea that this is our ratio, arc length to radius. Okay, let's do some more and then finish up. Okay, so this is very important now. It's all centered around changing the degree of opening of an angle to some measure of arc length and radius here, S and R. Okay, so if we say the measure of the angle here in radians is S over R, if we rearrange it, multiply across, we can say the arc length is R times theta. But theta must be in radian measure, of course, and that's the whole purpose of this unit. To say, wouldn't it be nice if we have a connection between the amount of opening and arc length and radius? Alright, so we can use this directly to find the arc length, just remembering theta can't be in degrees there, it must be in this ratio arc length over radius. Okay, let's do some. Circle has a radius of 10 centimetres. Find the length of arc of the circle subtended by a central angle of 150. Okay, so we've got a degree of opening in there in degrees. So first of all, to connect to arc length, to connect there, we need a radian measure. Okay, so let's convert over here now. 150 over 180 is 5 pi on 6. Or you might have saw there that 150 is 5 lots of 30. 30 is pi on 6, so 150 is 5 pi on 6. So now we know the measure of the angle. So radian measure is arc over radius. So 5 pi on 6 equals the arc length. And what's the radius? 10. Multiply across. We have 10 times 5 pi on 6 is the arc length. Arc length. Or over here, just use the new version of the formula. Instead of theta is arc length over radius, use the arc length equals r times, or radius times theta. So we would generally then make it 3 significant figures, actually 26.2. In the IB they have the rule or convention that you state your answer exactly, or to 3 significant figures, or as requested by the question, required by the question. Okay, notice that here, very important, the product r theta is the same as the units of r, because in radian measure theta has no units. Why has theta come up here? Why has theta got no units? Arc over radius is a ratio, if you like. The units cancel out, and you just get a ratio there. So that's an important idea. It doesn't contribute to any change in units. So if this is in 10 centimetres, the answer here, arc length, will be in centimetres. Okay, do you want to do some? Let's do one more here. The diagram shows a circle of centre O with radius 6. Now, I haven't got the diagram here. Let's draw the diagram in. Okay, so here, let's put in our axes, which is common here. Centre O and radius 6 centimetres. Angle AOB subtends the minor arc AB. So let's have a look. Maybe we will we'll just maybe get rid of this and just use A's and B's up there. So here, let's have a look. There's O and AOB. Let's say it looks like that. Do you understand this minor arc AB? That's the minor arc, because that is the angle subtending it. This arc is, if you like, sitting, or this angle is subtended by this arc. It's actually sitting on it. And here, this would be the major arc, the bigger portion of the circle, cut off by this angle AOB, if you like. So here, this is a minor arc, major arc. So the radius is 6 centimetres, and this is 10 centimetres. So we can make up our own diagram there. And that's pretty important in problem solving, to be able to do that. We don't need our XY coordinate system in there in this problem. So find the measure of angle AOB in degrees to 3 significant figures. So we're trying to find that, this time in degrees. Well, we haven't got a protractor, have we? So we're going to go in reverse now. We can say, well, here, over here, theta, the measure of the angle in radians, is S over R. Can we do it? Yep. 10 over 6, or 5 over 3 radians. And then we can say, well, 5 over 3 at radians, we could convert to degrees, because remember, pi radians is equivalent to 180 degrees. So we've got 5 over 3 divided by pi. We've got that fraction of 180. And so that's going to be our answer. That fraction of pi is that fraction of 180. So to change radians back to degrees, we're going to divide by pi, find how many, or what fraction of 180 we've got. Okay, and then that comes to approximately 95.5 degrees. All right, so you can go backwards. Just remembering, you'll use, I suppose, the system for measuring degrees or radians depending upon the given information. Here we were only given information to enable us to work out the radian measure. So flexibility is important in all this stuff now. Okay, come on down. We'll just revise some geometries of circles and things, because quite clearly now, in radian measure means you're going to measure arc lengths and radii and come at it from that point of view. So let's have a look at some things that might be helpful. First of all, the angle inscribed in a semicircle is a right angle. So if you've got a diameter here, right, so a straight line through the centre joining 2 points on the circumference, that's a diameter, and this angle is 90, because we call this top of the circle here a half semicircle. Okay, so it means that 90 is being subtended by the diameter. The line segment from the centre perpendicular to a chord bisects the chord. So if this is the centre and it's going to be at 90, then we know these two pieces are equal. That can be handy. And the tangent one, tangent to a circle, is perpendicular to a radius drawn at the point of tangencies, and also the two tangents from a given point or a common circle will be equal in length. So if we draw this tangent from P down here, then where it touches here, let's see at Q, then OQ will be at 90. The line from the centre, or the radius from the centre to the point of contact, centre to point of contact, will be at 90 to any tangent. It will be 90 to this tangent down here. From the centre to the point of contact has to be 90. And so due to the symmetry of the circle, of course, these two tangents are equal. And you could prove it using congruent triangles here. Might be a way of going for that second part, that second theorem there. So, yeah, remember the work of Euclid. These are Euclidean theorems now, and they can be handy in problem solving later on. So we're coming into looking at some circles, because that's where arc lengths and radii live. Okay, let's come on down and do a little bit more. Okay, well, there are some other results here that come out from radian measure, and one of them is to be able to work out the area of a sector. Do you remember this piece of pie in blue here is called a sector? Now, how are we going to find the area of that? Well, let's have a look. We can say, well, first of all, we know the area of the whole circle is equal to pi r squared. Okay. We have a portion of the circle. We have a fraction of the circle. Okay. What fraction of the circle do we have? Well, if we measured theta in radians, a fraction of the circle is theta 2 piths, isn't it? Because the whole thing around here is 2 pi in terms of radians. Okay, so if we change our angle theta to radians, this is a fraction of the circle we've got. Therefore, the area of the sector represented with the angle theta is going to be that fraction, theta 2 piths of pi r squared. We've got this fraction of the total area. Okay, let's do some cancelling here. So we've got a half, if you like, theta r squared. And we usually write as a half r squared theta. So there's a nice way of getting a simple formula for the sector. So the area of a sector is a half the square of the radius times the size of the angle, as long as this is in radians. Okay. So the best way of finding the area of a sector is to change this angle to radians. Then a half r squared times it will give you the area of the sector. It's all based on portions of the area of the circle. Okay, find what portion. Just remembering that an angle of 2 pi is equivalent to 360 degrees. Okay, so that's the notion there. All right, let's come down and summarise some of that now. Here we have it. The important thing here, the angle must be measured in radians, and then the formula becomes this simple one here. The area of a sector, remember what a sector is now. So here, piece of pie, okay, 2 bar there, into the centre, and out there. So there's our sector, any sector like that. Let's do one. Let's say this is 5 centimetres, and this angle looks like what? About 30, but we need it in radians. 30 is a 6 of 180, so it's pi on 6. So the area of that sector is a half by 5 squared by pi on 6. The angle must be in radians, because we've just used an approach in using pi's for revolution, so that would be our answer, and you can do that and put it in 3 significant figures at the end. All right, come on down, and here's their example here. A circle of radius 9 centimetres, has a sector whose central angle has a measure of 2 pi and 3. So it's a big one. Okay, what is that? 2 pi and 3. If you're still back in degree land, it's 2 times 180 on 3, which is equal to 120 degrees. Okay, so be flexible, be able to move between the two. So, can we find the length of the arc subtended? Yep, arc length is r by theta, which is 9 by 2 pi and 3, which is 6 pi. So the length of the arc is exactly 6 pi centimetres. So that's this here, around here, 6 pi centimetres. If you change it to a decimal, it won't be exact, of course, because pi is irrational. It's a non-terminating, non-recurring decimal, so you'd have to truncate it to 3 significant figures. So we'll leave it in the exact form here. And then the area of the sector is a half r squared theta, a half by the radius squared by 2 pi and 3, which is 27 pi centimetres squared now. Okay, why? Just have a look. Why is that centimetres squared? Can you see it? Well, theta has no units. It's a ratio. If you like, the two length units cancel out, arc over radius. But r squared is r by r. So yes, I think r by r. Centimetres by centimetres. So that will be where we get our square units from. Okay, centimetres by centimetres be centimetres squared. So that all is very consistent. Here is an important, it's not so much hint, I don't think, it's a very important point. You must have theta in radians, because we're now developing relationships like arc length is r theta, which only hold if we have the connection of the angle, not as an amount of opening. Not like that with degrees, but as a ratio of s over r. Then all these things come true. We're basing it all now on a measure of the angle theta being equal to arc length over radius, or s over r. Okay, so don't forget that. You can't put degrees in there, because that doesn't relate that angle to the arc length. All right. Come on down, and here's your chance to show your expertise here. All right, so there's about 33 of these problems. So what we'll do is what we usually do now is to pause it there, have a go, and then I'll show the next few problems and then the fully worked solutions. And in this work, I think it's necessary to do every one of these. These are important tools to have, working with degrees and radians and having a full understanding of them for further mathematics. Okay, so pause the presentation now and have a go. You might toggle back and look at some of the examples. Okay, where are the rest of them? Here they are here. 27 to 33. Yeah, we'll just come back a little bit. 27 to 33. Working forward and back from degrees and radians, from sector areas to arc lengths. Okay, so you can pause it there. I'll show you the solutions then, and then it's cheers from me. And I'll catch you in the next presentation, but let's go down and have a look at the solutions. Okay, that's 1 to 10 and down around 20 there. So they've put in all the working out there in the same way as what we did the examples. Let's go down now. I'm going to see a little bit further here. Okay, down to 26 and 31. And then the last few. Alright, so toggle backwards and forwards and checking your answers, and we'll go on with further excitement with trig functions in this unit, but for the moment, it's cheers from me.